let's just start saying that this is going to be like the last seminar of this volcanology course here at SCC. And so we are getting toward the end. And we have visited some place, even though not physically, but virtually. So we have been in Alaska. We have been in Costa Rica. We have been in New Zealand. And what the best place to finish all this seminars is to go back to Italy. And in particular, we are gonna be back in Campi Flegrei, the Flegreian fields. That means like land of fires. And you can see, like, back to me, this is a picture that I actually took myself. Those are the Serapis temple. It's a Roman, Greek, then Roman. Actually, it's not a temple itself. It was thought to be a temple, but then we then understood, like, from the archaeology, that actually was a sort of marketplace. And this marketplace had all, you know, you can go there, you can see all the little room there. Here was the butcher, here was the thing, so you can see everything. And you can also observe from my picture that there are some sort of holes in the columns here. And those are the lithodomes that have made their homes on the Roman marble column. And so from this kind of things, from this kind of evidence and record, they could actually understood how the ground was uplifting and downlifting, you know, especially at certain time. Those columns were just like popping up, like I think 1 meter and something off the ground before they were discovered. And actually they were used from a farmer to make vineyards. Okay, so and then, you know, there basically we're gonna listen now from Francesca. Basically the ground, we call that bradycism. So it's a slow movement of the grounds, up and down, up and down, up and down, up and down. And this is like, you know, like the natural response of our Mother Earth to breathe up and down and to produce magmas and to recycle volatiles and to scare citizen and also to give a very good soil. Okay, so let's now talk a little bit about Francesca. Francesca, she's, let me say, like, she's an amazing person and an amazing researcher. And she's now working in Singapore as actually a researcher, not a postdoc. Am I right? You know, sometimes when we talk about...
Yeah,
when we talk about those things. So she has been there for a little bit.
3 years.
3 years. And then she's about to basically start a tenure track in Italy, like I am gonna do, still in Milan, still, you know, but in another university. So we have competed together.
Oh, good.
And at the end, like, it was the best outcome. She got one position, I got one position. So everybody was happy. And but anyway, I mean, like, well deserved. Francesca has achieved a lot. If you look at her, like, publication record, I mean, like, think about, like, the presentation that she's talking about in a while. She was published in Science. And it has so much information. It's so dense of ideas. It's so dense of implications for future eruption in the Campi Flegrei, that has so many implications for the society. And but Francesca is not just like you know, a good researcher. She also had several awards for what she has done. She had a lot of funds. Especially like with the ETH in Switzerland, where she was awarded for a very prestigious postdoc fellowship. She also has 2 PhDs, like Sriparna 2 days ago, and like myself too. So you see that when you got 2 PhDs, this is the sign that you really, you really like what you're doing. Otherwise, you wouldn't jump twice on an adventure like that. So Francesca is definitely like very inspired and passionate researcher about volcanoes. And in fact, she has also a lot of background on field geologies about volcanology. She has mapped, she has done a publication mapping one of the Aeolian island that we will actually talk about in the beginning, at the beginning of our course when we were talking about myth and legends and the god of Vulcan. So she had experience in the field, she has experience in the lab, and everything is linked and go back to volcanoes and how volcanoes are forming and working. So I think I said everything, and probably I am missing a lot of other things, but without no further say, please, Francesca, go ahead with your seminar.
Thank you. So thank you guys for organizing this. I'm very happy to be part of this. And also I want to thank you for, can you see my screen?
Yes.
Okay, so I also want to thank you for getting up so early and being ready and active at this time of the day. To me, mornings are really dramatic, so I really appreciate the effort so much. And okay, so today, as Rosario mentioned, I'm gonna talk about silicic magmas and silicic magmas reservoirs and how they evolve. And I will focus mostly on the Campi Flegrei caldera that you see here in this picture. But I will also try to convince you that some of the models that we initially applied to Campi Flegrei are actually applicable to other systems as well. So one could ask, why silicic magmas? Why are silicic magmas so interesting? Well, silicic magmas, first of all, represent the most evolved and viscous melts that the Earth can produce. And they have played definitely a very important role in the evolution of our continental crust, but also on the volatile budget on our planet. And mostly for me, this part is mostly interesting, is that they are potentially explosive, and they have fed some of the largest explosive eruptions in the Earth's history. And here, in fact, I'm showing some examples of these eruptions, during which hundreds to thousands of cubic kilometers of silicic magmas were erupted during one single event. So due to all these reasons, it is very important to us as scientists to be able to answer some fundamental questions. For example, where and how silicic magmas are generated and how they evolve. In what conditions the silicic magmas are stored in the crust before they get erupted, and why they erupt, or why in some cases they don't erupt. So there is a general consensus, I would say, in the scientific community that magmatic differentiation in the crust is a polybaric process. And according to this model, starting from the lower crust where magmas get transferred from the mantle, so the mafic primary magmas get transferred from the mantle, they generally will tend to stall next to the moho, and they will start evolving mainly via fractional crystallization. And when the density of the residual melts is lower than the surrounding crust, the residual melt will start to rise towards shallower levels in the crust, and they will further evolve. But one very important aspect of this model is that in each of the steps of fractional crystallization and evolution, magmas will leave behind a solid residue. But it is in the upper crust where the final stages of fractional crystallization that lead to the most evolved compositions will actually occur. And in this environment, what happens is that these magma bodies will crystallize and will evolve further. And when the crystallinity of these objects, of these magma bodies, will reach up to 50 to 70%, then the convection in the magma chamber will cease, and the conditions will be ideal for the separation of the residual melt from the crystalline part, so the solid. And thus the residual melt will start rising towards the upper part of the reservoir, where they will start accumulating and forming lenses of crystal poor and evolved and very buoyant magma that is ready to erupt. But if the crystallinity of this system gets over the 70% crystals, that at least in these conditions, these magma bodies will be locked, will be rheologically locked in the crust. So this MASH model has radically changed our idea of how upper crustal reservoirs would look like from an early and now obsolete view of magma chambers dominated by liquid magmas. So in other words, seen as large pools of liquid magmas, to a much more modern view where these systems are much more complex and they are dominated mostly by solids, so by crystals, and where relatively small portions of liquid magmas can exist at the time. One very important feature of these systems is that they need, in order to thermally survive in the crust, they need to be very frequently replenished by hotter and more mafic magmas that come from deeper levels in the crust. And these magmas will play, as we will see, a very, very important role in determining the fate of these systems. So how do we know all this? So one very important tool that we can use to gather information about plumbing systems and magma reservoirs is to look at crustal sections that are exposed on the Earth's surface. And here I'm showing you a very famous example of a crustal section that is exposed in northern Italy in the Alps. And it's called the Ivrea Verbano and Serre dei Laghi section. And it exposes an exceptional crustal section that goes from the lower crust and even some mantle rocks to the intermediate upper crust and the associated volcanic rocks at the surface. And in this recent paper by Caracas et al., these authors used uranium-lead dating, high precision uranium-lead dating of zircons from all the different lithologies in the crustal section. And they use trace elements in zircon to demonstrate that all the lithologies in the crust, including the volcanic rocks at the surface, are both genetically and temporally, so chronologically connected. And this, of course, supports the idea of having a transcrustal mass zone that eventually fed the volcanic activity at the surface. However, although this is very cool to look at these crustal sections, these crustal sections are not very common on Earth. Actually, they are very rare. So generally, when we want to gather information about these systems, then we look at what is erupted at the surface during eruptions. And that's why one of the most important tools that we can use to do that is looking at large ignimbrites. Because large ignimbrites are pyroclastic sequences that are in place during large explosive eruptions, especially those that are associated with caldera collapses. And we assume that during those eruptions, most, if not all, the upper crustal reservoir gets evacuated during one single event. And so these large ignimbrites encompass a large variety of information about how magmas are stored before eruption, how they evolved, and potentially also how they erupt. So what is the trigger for these eruptions? So on this, during my PhD at ETH Zurich, I mostly focused on studying the large ignimbrites at Campi Flegrei caldera. And the reason why I did that is because Campi Flegrei is a recent caldera, so it's a quaternary caldera. And this is very important for the preservation of the deposits, obviously, because when we look at all systems, then the preservation of the deposit gets more and more difficult. So it's a very young caldera. And during this, the last 60,000 years, Campi Flegrei has experienced two large caldera forming eruptions. The first one at about 40,000 years is called the Campanian ignimbrite, and it erupted about 200 cubic kilometers of alkaline magmas. And the second one is called the Napolitan yellow tuff, and it's dated at 15,000 years, and it erupted about 40, so it's slightly smaller, cubic kilometers of alkaline magmas. The pyroclastic sequences that are linked to these two eruptions are very, very well exposed at Campi Flegrei, and the internal stratigraphy is very well studied. So it seemed to be a very nice place case study where we could study large ignimbrites. So for today's talk, sorry, I'll go back a second. So for today's talk, I will mostly focus on the Campania ignimbrite, which is the older and bigger of the two caldera forming eruptions. But I use actually a very similar method to study the Napolitan yellow tuff, and I got, with some differences, very similar results, and we will see it a bit more towards the end. But yeah, so today I'm mostly focusing on the Campania ignimbrite. So the Campania ignimbrite, it's a pyroclastic sequence that is zoned geochemically. So it is in the lower and intermediate part. So I would say the bulk of the sequence is represented by phonolytic compositions. And trachytic compositions, so slightly less evolved compositions, are only present in the upper part of the sequence. The mineral assemblage is dominated by feldspars, both sanidine and plagioclases, with minor amounts of pyroxene, biotite, iron titanium oxides, and apatite. Another striking feature of the Campania ignimbrite is that it's also zoned for crystallinity. So the highly evolved phonolites in the lower intermediate part of the sequence are represented by this crystal poor pumices. So pumices with about 5% crystals. Instead, the trachyte compositions in the uppermost part of the sequence are represented by these pumices that are highly crystalline, have many crystals. So they have about up to 37% crystals, so high crystallinity. If we now look at the glass geochemistry, so the matrix glass trace elements, we see that the crystal poor phonolites in the lower and intermediate part of the sequence are relatively enriched in rare earth elements, and they always have negative europium anomalies, which suggests that these magmas underwent quite significant feldspar fractionation that basically removed these elements from the belt. Instead, the highly crystalline trachytes in the upper part of the sequence are relatively depleted in rare earth elements, and they are always characterized by positive europium anomalies that instead suggest addition of feldspars to the melt. If we now look at the feldspars, we have that represent the most abundant phase, as I said. We have two kinds of feldspars. So we have a relatively low anorthite plagioclase that is practically unzoned and is in equilibrium with the melt. And this is coupled with a relatively low potassium sanidine that is also unzoned and in equilibrium with the melt. So this would represent the crystal that crystallized normally from our phonolytic melt. And then we have also some relatively high anorthite plagioclases that are quite zoned, as you can see. And they are found together with this high potassium sanidines that are quite strongly zoned. And these two kinds of crystals are only present in the upper part of the sequence, so in the least evolved magmas. If we look a bit more closer to these sanidines, we see that actually these bright rims in BSE images corresponds to a very high increase of both strontium and barium from core to rim. So we have cores that are partially resorbed, and they are overgrown by this very bright rim that have very high concentrations of strontium and barium, so up to thousands of ppm. We use our mineral chemistry, in particular the CPX, the clinopyroxene chemistry, together with the chemistry of the melt, and the sanidine plus melt chemistry to derive the magma storage conditions in terms of temperatures and water content. And to do that, we use geothermometer and hygrometers that are calibrated to these specific alkaline compositions. And what we observed is that we have an increase of the temperatures and the decrease of the water content up sequence. So to summarize this information, we have a pyroclastic sequence that is zoned for chemistry. So we have a decrease of the degree of magma evolution up sequence that is coupled with an increase of the temperature and the decrease of the water content and an increase of the crystallinity. And we have glasses with positive europium anomalies here in the upper part of the sequence. together with high anorthite plagioclases and high strontium and barium sanidins, only in the upper part. So now we can use all this information that we got to come up with a model that can explain how we generate all these variations and these gradients in our magma body. So we start with our upper crustal magma reservoir that is evolving via fractional crystallization. So we have our alkaline magmas that starts crystallizing, and they will produce a crystal mush, so an area of high crystallinity, which in this case is dominated by feldspars. And then when the crystallinity of this crystal mush, as I said before, reaches up to this 50 to 70%, then the residual melt can be extracted, and they will start accumulating, forming this lens of crystal poor magmas in the upper part of the magma chamber. And then, as I mentioned before, these magmatic reservoirs are often and frequently interested by these recharges operated by more mafic magmas of deeper origin. So these magmas bring into the system these high anorthite plagioclases. But they will also be much hotter than the resident magmas. So when they pond at the base of the magma chamber, they will trigger the melting of the low temperature phases. So in other words, the feldspars in the mush. And this melting will generate a residual melt that is, sorry, an interstitial melt that is enriched in all the elements that are that are very enriched in this feldspar. So in particular, strontium, barium, and europium. And when the temperature decreases slightly, then these feldspars will crystallize again, but will have much higher strontium and barium content because they derive from these anomalous melts. Okay, so we will have this high strontium and barium risk that they will overgrow this partially resorbed cores. And probably one of these recharge events, maybe the last one, actually triggered the eruption of the Campania ignimbrite that involved during the initial phases only the upper part, so of the magma chamber where the crystal poor and highly evolved melts were. And then during the later phases of the eruption, probably also part of the more crystalline portion of the magma chamber, so the roots of the magma chamber can be erupted thanks to this partial melting that reduces the crystallinity. Because when these mushes are so crystalline, as in the first cartoon, then they are, as we said, they are rheologically immobile because their crystallinity is too high, and so they can't be remobilized. But when the mafic recharge triggers the partial melting, then it reduces significantly the crystallinity, and this allows part of the roots to be erupted, and this will produce at the surface our zone ignimbrite. So after we applied this model to the Campania ignimbrite, actually we also wanted to test if this model was applicable to other ignimbrites, and so we compiled a series of, a large data set that included a serious number of ignimbrites from all around the world, from different tectonic settings and with slightly different compositions. So not only alkaline magmas, so similar to those that were erupted at Campi Flegrei, but also rhyolitic compositions. And, but all these ignimbrites actually have similar characteristics to the Campi Flegrei one. So they are zoned for composition, and they have quite a range, they display quite a range in crystallinity, and also they are zoned thermally. So what we observed is that in all these cases, as we saw for the Campania ignimbrite, the early erupted magmas were those characterized by low barium contents and negative europium anomalies. So the most evolved melts, mostly crystal poor, that experienced a lot of feldspar fractionation. So those melts that were sitting on top of the magma chamber. And instead, during the late phases of the eruption, the high barium magmas with positive europium anomalies, so those representing the partially molten crystal mushes, so the roots of the magma chamber, could get erupted. So actually this partial melting of cumulate seem to play a very, very important role in triggering this kind of big eruptions. So after looking at the two caldera-forming eruptions at Campi Flegrei, we also wanted to look at the evolution of the system as a whole during the last 60,000 years. And the reason why we wanted to do that is because Campi Flegrei is, after the last caldera-forming eruption, which occurred 50,000 years ago, has undergone a period of very intensive activity, which stopped with the last eruption of Monte Nuovo that occurred in historical time. And after that eruption, Campi Flegrei has started a phase of quiescence, which is although punctuated by several episodes of unrest. And so it's very difficult when we deal with active calderas to interpret these signs. And so it's very important to understand at what stage currently Campi Flegrei is, in order to make prediction how Campi Flegrei will behave in the future. So actually, by looking at this 60,000 years of activity, what we wanted to do, we wanted to test the hypothesis that was actually formulated by Pete Lipman in the 80s. And this is his original cartoon, that caldera-forming eruptions, especially those that have experienced more than one caldera-forming eruption during their history, they can follow some cyclic paths of activity that accompany the phases that lead from one caldera-forming eruption to the other. So basically, we wanted to look at how this magmatic system approaches a caldera-forming eruption and how a magmatic system recovers after a caldera-forming eruption. This is obviously a very interesting approach, as you can imagine, but it's very limited to the amount of data that we have, because most caldera we deal with don't have very solid stratigraphic reconstructions, just because it's very difficult when we have large eruption to have a stratigraphic record from the previous activity that is preserved in these calderas. And so in order to have a complete, let's say an overview of the activity of the caldera, we need to have a record of all these phases of activity, not only of the big eruptions. So actually, again, Campi Flegrei instead represents one of the systems where exceptionally we have a very good stratigraphic record, and it's very well studied. So we have ages, we have petrological data, we have stratigraphic reconstructions. And so that's why we, in order to look at the evolution of the system as a whole, we went to Campi Flegrei and we sampled 23 eruptions. So including not only the two caldera forming, but also eruptions that were representative of the phases that preceded and followed the two caldera forming eruption. And of course, also of the last period of activity. So the last 15,000 years of activity, including the last eruption of Monte Nuovo. Of all these eruptions, we obtained new petrological data, and we looked at some proxies, and in particular, and we look at the variation of these parameters with time. So here I'm showing some of these parameters. First of all, the DI, which stands for a differentiation index. It's an index that is used very frequently to define the degree of evolution of alkaline magmas, similarly to the silica content for rhyolitic magmas, in other words. And here we have time. So time decreases to the right. And as you can see, we can see some interesting trends. So here we have the two caldera forming eruptions, and we see that we have an increase of the degree of magma evolution before the two caldera forming eruptions. After the first caldera forming eruption in particular, we have less evolved magmas that characterize the first phases of activity. And then with time, magma will tend to evolve towards the second caldera forming eruption. A very similar trend can be observed after the last caldera forming eruption. So in the last 15,000 years of activity. So initially more mafic magmas that then tend to evolve with time. And in our last eruption, historical eruption of Monte Nuovo, the geochemical characteristic of the eruptive magmas are very, very similar to those erupted before the caldera forming eruptions. So for what concerns the crystallinity, we see quite a lot of scatter, and we will discuss in a bit why. But what I would like to point out here is that coupled with the degree of magma evolution, the crystallinity tend to decrease before the caldera forming eruptions, and is very low in the last eruption of Monte Nuovo. Okay, so now I'm showing you the variation of some geochemical parameters in the matrix glasses again, in a barium versus europium anomaly again. So the barium and europium anomalies mostly are indicative of feldspar fractionation, which is the most abundant phase at Campi Flegrei. So it's the one that drives the composition of the liquid when it evolves. So we start from here, from the upper part, where we have the most mafic magmas that were erupted at Campi Flegrei. So those that were erupted after the caldera forming eruptions. And they plot here at high barium and slightly negative europium anomaly because they haven't experienced so much of feldspar fractionation. So when these magmas evolve towards more evolved compositions, they will move along this line. So the barium will start decreasing because it will go into the feldspars, and the europium anomaly will start to get more and more negative because the europium will also go into the feldspars. So the most evolved liquids actually will plot down here at low barium and very negative europium anomalies. But as you can notice here, we have a group of blast compositions that actually plot out of this main trend. And these compositions that have positive europium anomalies and intermediate barium contents are actually referred to the, actually only present in the caldera forming eruptions. And as we saw for the Campania Nigrinbrite, they represent these melts that derive from the partial melting of the cumulates, okay? So these melts are only present during the caldera forming eruptions. So similarly to what we did for the Campania Nigrinbrite, we derive temperatures and water contents using the same tools. The difference is that here we are looking at the variation of these parameters over time. So again, time decreases to the right. So as you can see, here, similarly to what we saw in the degree of magma evolution, we see some trends. So we see that we have a decrease of the temperatures and an increase of the water content before the first caldera forming eruption, and the similar trend before the second caldera forming eruption. So decreasing temperatures, increasing water content. And after the second caldera forming eruption, so again, in the most recent activity, we see a very similar trend. Although with some scatter, we see a very similar trend. So decreasing temperatures, increasing water content. So again, we can use all this information to come up with a model for the caldera, the cycles of activity at Campi Flegrei, which starts in this case with the caldera forming eruption. Okay, so similarly to what we saw for the Campania Nigrinbrite, we can extrapolate it to the Napolitan yellow tuff. I didn't show you, but trust me, it was very similar. So we have our upper crust reservoir with the extracted melts on top of the magma chamber and the crystal mash. So we know that during this large event, not only the upper part of the reservoir with the most evolved and crystal poor melts gets erupted, represented by these compositions down here, but also the lower part and more crystalline part of the magma chamber gets erupted, represented by these other melts. And it produces zone Nigrinbrite. After the caldera stage, in the early post-caldera stage, we continuously have recharges from deeper levels operated by more mafic and hotter magmas and so you can see that after the caldera forming eruptions, we have these more mafic magmas coming out that are also hotter. So they also have higher temperatures. And these magmas will erupt relatively easily because they will take advantage of the faults, of the fractures that form during the caldera collapse. But some of these magmas will actually stall in the residual crystal mash, and they will interact with some of this crystal mash. So that's why during this period of activity, we have magmas with higher crystallinity. But these magmas that will stall in the residual mass also will, as time goes by, they will start evolving toward more evolved compositions. And finally, in the late post-caldera stage, all these batches of magmas will tend to coalesce, and they will form again a large upper crustal reservoir, which will be characterized again by very evolved compositions, very low crystallinity, because we will have again a mash system from which the low crystallinity melts will start to get extracted and rise to the upper part of the chamber. And so these melts will be relatively cold and relatively water rich, because as we will see later, also volatile will start accumulating. And at this point, we can have two ways where the evolution of the system can go. So either it will passively degas and die, or it will start a new cycle. And this is what potentially happened at Campi Flegrei in the second cycle. So when the system evolved toward the second caldera forming eruption. But then at this point, since we saw that during the last period of activity, so after the Napolitan yellow tuff, we saw similar trends to the ones observed in between the two caldera forming eruptions, it became very important to look a bit more in details at this last period of activity to find out more about the current status of the magmatic system. And to do that, we coupled our petrological data with a thermomechanical model. And honestly, not being a modeler myself, for this part, I had to rely on I relied, and I was happy to do that, sorry. I relied on the expertise of a colleague who is Wim de Gruyter, who is the scientist that actually developed this thermomechanical model of magma chambers in the first place. And Wim was actually very good in adapting his model that was initially a general one to the conditions for Campi Flegrei. And so there are many parameters that feed into this model. And it's a very complicated model, so I'm not gonna go into details today, but what I wanted to point out is that one of the most important parameters that goes in this model is the overpressure that is necessary to trigger an eruption. So this overpressure value is not very well constrained. And so that's why in our model, we use different values of this overpressure. And we obtain different runs for this model using different values. And here today, I'm only showing you our best fit that was obtained with an overpressure of 40 megapascals. That is actually a value that is used very frequently in the literature. But what does this mean? So this represents the overpressure inside the magmatic reservoir. And we assume that when the overpressure in the magmatic reservoir reaches this 40 megapascal, the reservoir is pressurized enough to trigger an eruption. So in this panel here, what I'm showing is that each of these wiggles correspond to an increase of the overpressure in the reservoir. And when each of these wiggles reaches the top of the graph, we reach the 40 megapascals, so we have an eruption. So as you can see, so this represents the last 15,000 years of activity. So again, we have time here. And we will see that during this period of time, Campi Flegrei had 3 epochs of activity, during which the activity in the caldera was very, very high. So we have many, many eruptions during this period of time. And using this overpressure of 40 megapascal in the model, we could reproduce almost exactly the number of eruptions that we had during each of these eruptive epochs. Despite this very high frequency of eruptions during this period of time, the total volume of the reservoir slowly increased with time. And the temperatures instead tend to decrease with time. And this trend of decreasing temperatures reproduces quite well the trend that we observe in our geochemical data that are represented here by these bars. Instead, this line represents the output of the model. And the water content instead tend to increase. And there is very important observation in this graph, in the water content graph, that at Monte Nuovo, so during the last eruption at Campi Flegrei, the water content was so high that it hit the saturation, which means that sometimes before the eruption of Monte Nuovo, an exhaust volatile phase, so in other words, like bubbles, started forming in the reservoir. And this has a dramatic influence on the physics of the reservoir. Because when we have an exhaust volatile phase in the reservoir will become much more compressible, which means that if we inject volumes of magmas from recharge into the reservoir will be prone to accept these volumes of magmas without getting to the overpressure that is necessary to trigger an eruption. So in practice, when we have exhaust volatile phase, we don't have eruptions, so the eruption frequency goes down, and we have magmas getting into the reservoir. So the reservoir will start growing. And we think that this is the reason why, after Monte Nuovo, Campi Flegrei entered a new phase of quiescence. That doesn't mean that the system is dying, but it rather means that the system is growing. So to summarize this part, we have identified petrological cycles at Campi Flegrei that always lead towards the generation of highly evolved, crystal poor, relatively cold and water-rich magmas that are erupted during small eruptions that precede the caldera-forming eruptions. And these magmas are very, very similar to those that are erupted during the initial phases of caldera-forming eruptions. The eruption of Monte Nuovo, we observed that has the very similar characteristics to these magmas that were observed before the caldera-forming eruptions. And the results of the thermomechanical model coupled with our petrological data would suggest that the eruption of Monte Nuovo represents a turning point in the evolution of Campi Flegrei that might coincide with the start of a growing phase for the system that might potentially culminate in the future in a new caldera-forming eruption. So in more recent times, after I applied this model to the Campi Flegrei caldera, and we saw that actually there are some cyclic patterns that we can recognize. Together with my current supervisor, Caroline Bouvet, and my previous supervisor, Olivier Bachmann, we tried to apply this concept of caldera cycles to other systems to see if we could make it more generalizable. And so again, this approach is very limited to the fact that there are not so many caldera forming systems that have the same characteristics that Campi Flegrei has. So such very complete geological record and so many petrological data available or that are easy to get. So that's why for this, we identified 4 caldera forming magmatic systems in addition to that we studied in addition to Campi Flegrei. And these are young, relatively young systems. And 2 of those, the Kos-Niziros volcanic center in Greece and the Long Valley caldera, actually only experienced 1 caldera forming eruption during their history. But this was a very positive thing for us because it allowed us to look closer to the phases that start a caldera cycle, which is very difficult to see and to observe in the systems that have experienced more than 1 caldera forming eruption, because this system being very active, the phases of activity, so the products that represent the early phases of activity are most probably buried underneath the younger deposits. So it's very difficult to observe this part of the cycle. So that's why having these 2 systems was very interesting. And then we also added the Rabaul caldera in Papua New Guinea and the Okataina volcanic center in New Zealand, which are instead calderas that have experienced multiple caldera forming eruptions, so similar to Campi Flegrei. And this allowed us to come up with a much more complete caldera cycle, which starts from the incubation phase that we can only see in those systems that have had only 1 caldera forming eruption, because it's only preserved there in the record. And this incubation phase corresponds to the onset of the volcanic activity in a given area. And it's a very important phase that can last, according to the thermal model, up to 1 million years. And it corresponds to a phase where basaltic, so mafic magmas get injected for a long time into the upper crust. And this phase is very important because it primes the upper crust to host a magmatic reservoir. So when the upper crust is cold, it's very rigid. And so it's impossible for the magmas to stop there and to form big reservoirs. So the magmas will just transit into the crust and will get erupted right away, or they will get frozen in the crust. So we need the crust to be less viscous and hot, like warm, in order to be able to host a reservoir. So this is the incubation phase. And when at the end of the incubation phase, we actually have the crust is warm enough. So we will start having some small reservoirs in the upper crust, while the magmas from the mafic composition will start to evolve towards more evolved compositions. And during this phase that we call the maturation phase, most probably there is not a big reservoir yet. So these magmas will probably evolve in small batches. So they will have some differences in the geochemistry, especially in the trace elements. Although in major elements, they might be very similar, they will have some small differences because they will evolve in a slightly different way inside the small reservoirs. But at the end of the maturation phase, all this small reservoir will eventually coalesce in a large reservoir, and a mash system will start forming. So we will have, because these magmas are evolving by fractional crystallization, so they will deposit their crystal cargo at the base of the chamber, and some melts will start to be extracted and accumulate in the upper part of the reservoir. At the end of the maturation phase, as we saw for Campi Flegrei, there is a very important step in the caldera cycle, which we call now the fermentation phase. So this phase corresponds to the constant presence of an exole volatile phase in the reservoir that again will dramatically change the physics of the reservoir and will allow the reservoir to grow. So during this fermentation phase, actually the reservoir will start a runaway growing phase that will only be stopped by the caldera forming eruption itself. And during this phase, so when the volatile phase, the exole volatile phase is present in the reservoir, it's actually very difficult to overpressurize the reservoir because the reservoir will be so compressible that it will just accept all the magmas that come in. So there are several processes that actually can overpressurize the reservoir. So for example, one process could be that the magmas are still crystallizing, and so they are still accumulating and exsolving volatiles. And so overpressurization of the reservoir could just come from protracted crystallization. Or there could be an increase of the recharge, because the recharge will bring new magmas, but will also bring more volatiles into the magma chamber, and so will contribute to pressurize the magma chamber. And actually the analog models of dike propagation in the crust have shown that when there are big reservoirs in the upper crust, they will tend to attract more dikes. So it's possible that during this phase, the recharge increases. And finally, as we already saw and mentioned multiple times, probably the mash melting. So the recharge will start melting some of the crystalline part of the reservoir, and that will decrease the density of the magmas in the reservoir, and so it will enhance the buoyancy of this melt. So these melts will become less dense, and so more prone to erupt. So all these processes probably combined together will lead to the caldera forming eruption. After which, so during the caldera forming eruption, we have the failure of the roof of the magma chamber. So the system will completely open. It will depressurize massively, and that will trigger more crystallization. So actually it will be after caldera forming eruption, the remaining part of the reservoir that didn't erupt will be very, very crystalline. So at this point, it's very, very important that we have continuous recharge to keep the system alive. Otherwise, the system will just freeze in the crust and the cycle will stop and the system will die. So if we have enough recharge, instead, we will go to a recovery phase. So we will have recharged magmas entering the reservoir and rebuilding the reservoir, and the cycle will restart. A very important observation is that during the second round, the system won't go through the incubation phase. So it's typical that during the second round, that the second round could be faster than the first round, okay? So I'm just showing to conclude just few examples. So this is the Long Valley caldera. So as you can see here I'm showing, so time, this time is going to the left, sorry. And here I'm showing now the silica content, so the degree of evolution of these magmas. So as you can see, we have this incubation phase during which we corresponds to the first phase of the cycle, which corresponds to the injection of this mafic magmas in the upper crust. And as you can see, this matches quite well with what with the duration that is suggested by the thermal model. So actually this phase lasted about 1 million years. So 1 million years of injection of basaltic magmas in the crust, priming the crust to host the reservoir. And the transition to the maturation phase is marked by this abrupt transition toward towards more and more compositions. And as you can see, during maturation and fermentation phase, we will have already very evolved compositions. But if we now look at the trace elements, we see that during the initial phases of the maturation phase, these magmas are quite heterogeneous in trace elements, but they will tend to get more and more homogeneous when we approach the caldera forming eruption, here marked with the red line, okay? And another quick example. So this is the Okataina. So as you can see here it was quite challenging because there is not, the availability of petrological data is not great, especially for the intermediate cycles of activity. So most of the data are actually referred to the last phase of activity. So after the last eruption, last caldera forming eruption. So as you can see here, similarly to what we observed for Campi Flegrei, after the caldera forming eruption, we can see the recovery phase. So where we have more mafic magmas injecting into the system to reconstruct the system, and they will evolve through time, again, similarly to what we saw for Campi Flegrei, towards more evolved compositions, similar to those erupted during the caldera forming eruption. So if we take now a simplified version of my first panel in the thermomechanical model, in the evolution of these reservoirs, we can identify two main stages. So one that we can call the blow stage and one that we can call the grow stage. So the grow stage would correspond to the recovery or the incubation phase, where we have very frequent eruptions and we don't have a volatile phase in the reservoir. So the reservoir will be easily pressurized every time we have recharge, or almost every time we have recharge. But then when the magmatic volatile phase will exsolve and will be stably present in the reservoir, the frequency of eruption will diminish, and we will enter this growing phase of the reservoir. Okay, that corresponds to the end of the maturation phase and our fermentation phase that will lead to the caldera forming eruption. So if now I go back to one of my first slides to conclude, I hope I convinced you that we know where and how silicic magmas are generated. We know in what conditions magmas are stored in the crust before being erupted. So mostly in highly crystalline form. And I think we still need to do a lot of work on constraining a bit better the timescales of all these processes. So how long they are stored before getting erupted. And I think we have an idea of why they erupt. And as we saw, we think that it's possible that more mafic recharge is one very important trigger, but also cumulate melting, as we saw, could play a significant role in triggering this kind of eruptions. And with this, I conclude, and I'm happy to take questions if you want.
Okay, thank you, Francesca.